Okay, folks, let's talk about the Michaelis-Menten equation. It's given to you here at the top right of the screen, but what I want to reinforce for us today is that I'm not super focused in on the math for this. Just like with hemoglobin, it's important that we can read a graph, that we can understand a graph, but your ability to do math is not what I'm testing. Your ability to understand the big ideas is what we're focused on today. So let's try to keep that in mind as we discuss this graph. Let's first just orient ourselves to the graph. It is hyperbolic, kind of similar to that myoglobin graph that we learned a while back. The y-axis is v0, initial velocity, and its units are moles per second. And remember that we want to be doing this when there's a lot of substrate, kind of on this graph that we pointed ourselves to. We want to make sure that we have lots and lots of substrate to enzyme to make sure that the setup is correct. Let's jump real quick now to the x-axis, S. This is the concentration of substrate. Its units are moles. And now, some interesting aspects of this graph that will kind of seem like a throwback to the hemoglobin and myoglobin discussion. So we have Vmax. This is the maximal velocity that the enzyme can reach. Think of it kind of like its speed, how fast it can do the chemistry. Units are moles per second. And then finally, we have a constant that looks like the K constant we discussed with hemoglobin, but here it's called Km, the Michaelis constant. Its units are moles. It is the substrate concentration at 1/2 of Vmax, and it tells us how well an enzyme binds its substrate. This is very similar to the hemoglobin and myoglobin K value, which was K, how well that the hemoglobin, for example, binds oxygen, and its definition was the partial pressure of oxygen at 1/2 saturation of hemoglobin. Well, here we have Km, which is the concentration of substrate at 1/2 maximum velocity. So for example, if we're looking just at a typical graph of kinetics, we can find this Km. First thing we do is find 1/2 Vmax on the graph. So if this is 1 Vmax, this is 1/2 Vmax. We can take this to the right where it hits the curve, and then drop it down to the bottom here where we have Km. And with Km, we'll think about a very small Km as being the enzyme binds well, or the enzyme binds tightly to its substrate, whereas a large Km is an enzyme that binds poorly or weakly to its substrate. But sadly, there is more to know about enzymes than just Km, which is how well it binds, and Vmax, which is how quickly the reaction happens. There is an additional variable called Kcat, and really, this is a preferred constant to use when comparing how quickly enzymes perform their reactions. Because, as shown here on the right-hand side, Kcat divides the Vmax by the enzyme concentration, okay? So why is this important? Well, let's say you're in the lab running a reaction with your beaker of enzyme, and your buddy next to you is using 3 times as much enzyme. Well, they will likely see a bigger Vmax than you will see because their enzyme can convert a lot more substrate to product than your enzyme. So Kcat is what we'll use to kind of compare enzyme velocity, the catalytic or rate constant. Its unit is slightly different. It is just per second because we have divided moles by moles, so the molarity is out of the picture now. And so this really tells us how many reactions can this enzyme do per unit of time. And it is a better constant to use when comparing velocity. Now, finally, we have kind of the overall catalytic efficiency. And this is the best way to compare enzymes because it takes into account both the velocity and the binding. So catalytic efficiency is equal to Kcat divided by Km. The largest possible catalytic efficiency is between 10 to the 8 and 10 to the 9 per mole per second because this is controlled by diffusion. And so an enzyme cannot possibly be faster than how fast the substrate can get to that enzyme. And so as a general rule, efficient enzymes have a very large Kcat. That means they do lots and lots of reactions quickly, and a very small Km, which means that they only need a tiny, tiny amount of substrate to do that reaction, which means that efficient enzymes have a large Kcat over Km value. Next up, we'll learn one additional way to look at Michaelis-Menten kinetics in a graph that thankfully is linear and not hyperbolic.